bring everyone on the same ground. So we're going to talk about, data reduction. And, because, so this is like a common misconception, like you can just buy a bigger computer or make a faster algorithm, then I can deal with all this data that I have. But it's never true because, you'll always, in practice, data will always grow more than you can buy the hardware or you can design algorithms, right? There will always be more data. It will always grow more than what you can buy. So you always have to think about reducing the data, always. You're never ever going to be enough of assistive help. Okay, so you're going to do like, we talked about this random sampling, stratified sampling, and the dimensions you're going to do by transformation or dimension elimination. And oftentimes you actually have to do both, right? You have to reduce the dimensions of the attributes and the samples at the same time, either together or one by one, okay? And, so basically for this, you need to figure out like which samples to discard. So the good candidates are basically redundant data. We talked about this last time. So, if you go to a store, usually don't buy all the ravioli cans they have. You only buy like a one of them, and you're going to pick them depending on importance. So maybe pick 2 of these tiramisu boxes and so on. And we talked about this before, right? So, you'll have like many different data, and oftentimes they're not like nicely organized like this. They look more like this, right? So it's basically someone gives you some data, they're totally disorganized. You don't know how to pick them. So what you're going to do is like you have to come up with some sort of measure how to compare these data points. In this case, these clothing items. So you can sort of start binning them nicely in a nice shelf, right? You have to figure out which are the sweaters, which are the pants, and so on, and bin them. So now you need to somehow describe them. You need to describe them in some way. Okay, and this is what's called feature vector, right? You have to come up with a feature vector. So for example, here, these are 2 pants. Actually, these are 3 pants. All of them are long pants. Only here is a short one, but this is still different. Pant is different than this one. So you got to come up with some way to describe this pant and make it distinguished from another pant, so you can see the difference. So, need a measure of similarity. Okay. So, and once you have the similarity, you can figure out, you can distinguish them in high-dimensional feature space. Okay. So you've got to make this feature space, and you make it like length and ornateness. I basically picked ornateness to distinguish the different pants. And then I picked also length to distinguish the different pants. So these seem to be good features. They're sort of nicely discriminatory. So now these pants are sort of grouped together, same length, but not the same. And this one has a similar length, but has very different degree of ornateness. And this guy here is shorter. Okay, so now you've nicely identified 3 clusters of pants, and they're nicely distinguished by these 2 features vectors here. Had you chosen only length and color, then probably these 2 guys, color, they would have been together here, right? And then it wouldn't be so nicely, because these are very similar pants, just in different color. But this is a very different pant, right? So you got to figure out what is this this sort of attribute that you want to use. Okay? So we did not consider color, texture, or size because none of them would have nicely distinguished them as much as the length versus. Okay. So measuring similarity can be difficult. For example, when you look at these 2 pictures, they look very similar, right? I mean, the color is the same, the sort of similar hair, a little bit different here, maybe this nose is. Of course, you as a human quickly see it because you have a very complicated pattern recognition system in your head. But as a computer has a much harder time. Computer has to learn what makes this woman different from this dog, right? So that is that's a difficult task. So measuring similarity can be difficult and maybe complicated, right? There may be many different features with the computer at the time. So let's look at the similarity functions, right? For example, it's used oftentimes in product recommendation systems. And you have like this guy here, who often buys pizza and salad, buys a can of diet soda. And now this guy comes here and orders something from you, and you want to recommend him something else. And then you know, okay, this guy orders pizza, he orders salad, he orders salad. Okay, what else can I recommend this soda, right? So they recommend that too. So because these two guys were very similar, they're only different in this part of this drink. So, you could like sort of make associations. So it's a very, very, practical thing to know. Okay? And of course, you want to make sure similarity works, right? So if similarity function isn't working, then you recommend the wrong thing. Maybe this guy, this guy, if you have the wrong similarity function, you may recommend this guy a beer, although he doesn't want to have a beer, right? He wants to have a Coke, just like that. It's very important that you similarity function. Okay, so you need to actually measure this. So you make a feature vector in terms of the pant, you make length, domains, color. In terms of the food, you make type pizza, type drink. These are basically your feature vectors. And then you'll have different examples. And you express them a number. Long is like 30 inch, plain is ID 1, pan is ID 2, short, this one is 15 inch, ornate is ID second, and blue is 5, right? Basically express it in numbers, encode these textual descriptors that appear, in categories, encode them in numbers, and then make that a nice numerical feature vector that you can cluster. Okay, and of course you can do the same thing. Okay, so now as you want to cluster things, you want to sort of figure out how do you measure those differences? So a simple way is using this method. Like B and B, essentially we just take measure the difference that one along the axis plus the difference of this axis, add it all. That is basically a method. Okay? Euclidean distance is this. Then you take the short this squared plus this squared plus this squared. Then basically this describes this the growth. It's a little more direct the distance. It does a little bit more potential, but it's basically what it does. It emphasizes so we'll have like bigger this basically bigger the so no matter raise it to half the power, or square root, or third root, just depending what power you use, you can bring out differences of a certain scale. Okay, so this gives you this. It's called like a norm, basically. And then cosine similarity is another one where you measure the angle between two vectors. So the first thing you would do is you make both vectors the same length. Essentially, you divide them by the length they have, and then you measure the cosine. The cosine essentially is just the dot product of the two. It's just the dot product of A and B. That is essentially divided by the length of the vectors. Then you get the cosine distance, okay? Which is not the angle, it's the cosine of the angle. So the bigger the smaller the angles are, so the bigger the angles are, it gets less sensitive, right? So differences in faraway differences in terms of angle get less and less pronounced, okay, because of the cosine function. So again, you can also use another function. You can just use the angle itself. That's much less biased in terms of the difference. So it just depends, right? Pearson's correlation is this one, where you use correlation. So eventually, it's very similar to the cosine difference, but the only thing that's different is you divide by the standard deviation of these different axes. So this is basically find the mean of it and subtract x is number 1 or subtract x number 2. It essentially tells you basically how much these two dimensions, the distribution of dimension values really match. Okay, correlation similarity. So this is the mean across all the variable values for data item x and y. Data item x, data item y. This is the mean of all the variables values. So basically, this finds the average. This is the average looking pair of pants or shoes. Okay. So now, okay. Turns out the correlation distance is a little less strict than the cosine distance. Like this is correlation. They will have the same distance, right? So this is basically these red and these green and blue lines. They will have the same distance. While in cosine it would be not the same, because the cosine divides by the mean, so it makes the mean. Instead, the mean actually is taken out. Like the blue and the green have different means, but the cosine distance takes it out, and so a correlation takes it out, but not the cosine. So Jacquard distance is another one that is basically more a set kind of distance, where you try to compare different sets if they're the same. Okay, so basically you compare the intersection of set A and B and divide it by the union of A and B, or basically it's the magnitude of A and magnitude of B minus the intersection of A and B. So here's an example of it. Jacquard distance of that distance essentially is this. If you have these two baskets, basically, intersection is 3. Intersection is 3, and the lemon and the strawberries and the lime, right? Those are shared, and all the others are different. Okay, and then basically that you compute. This is basically good for sort of itemized lists. And that would be the way to do it. Now you organize the shelf, make that shelf this one, and you use clustering for that. Okay, so you basically use a clustering method. You try to use the similarity metric and try to figure out which items belong together, and then you take them and put them in the shelf. Okay, so what is clustering? Many of you probably know this from the data science course, but for those who didn't take the data science course, I'm going to explain it. So basically what happens here is you're going to try to find out, which things go together. Okay, and here we basically, in data mining, really similarity and distance are really the same things. Okay, like similarity is basically, distance basically is getting larger the less similar they get. So the higher the similarity, the smaller the distance. Okay, so it's always 1 minus that, right? The higher similarity, the smaller the distance. So now let's cluster this. Clustering basically groups similar items together. So basically you group these together, and then you group this one. It's easy to group, there's only one, and then you hierarchically merge them. So now you group these two clusters together, and eventually you group all of them together, right? So basically this is a hierarchical clustering technique, where you try to group very similar things together, then you broaden the scope and group less similar things together and broaden even more, and eventually you have clustered entire things, like a hierarchical cluster. So what's a good cluster? Basically, a cluster is a group of objects that is similar. Okay, so basically dissimilar from other groups. So so we need some sort of objective function that captures this mathematically in terms of like the overall cluster, the overall grouping that you have achieved. You got to score it. Okay, so there's like an overall grouping that I achieved, and you want to give it sort of a score how well it has grouped your data. And if the score is not good, you're gonna try another grouping and see if that's better, right? And you can sort of capture that quality of the grouping and optimize for it, in an iterative algorithm. So one way to judge clustering is the mean squared error. Okay, and so I'll explain you how this works. Oh, sorry, I'm going backwards. So the mean square error basically, you can optimize for that. Okay, but the problem with the mean squared error is it's a global, if you have a clustering, it may not be, you want to basically find a clustering that has the smallest mean squared error, but sometimes you may not reach it. Okay, you may only go in a local minimum here, and you just can't go further. And then because you're stuck here, and you can't climb yourself out and go to another minimum or another one. So you need a little bit of a technique that avoids this, right? That sort of rescues you from these local minima and brings you in a global minimum. So there's like techniques like simulated annealing, which jump around a lot in the beginning and then jump less in the end towards the end. Or you're gonna run the clustering multiple times and see when you get the best mean squared error. There's all these kinds of techniques, and there's really no real good, really perfect solution for it. There's always, you have to basically try and error and find out what they are. There's some techniques are a little faster in finding, and some techniques are not so fast. So let's talk about one particular clustering method, okay, which is k-means clustering, which is the most famous clustering method and still probably the most widely used. And to tell you the truth, it really does work not too bad, okay? From a practical standpoint, k-means is not a bad method, okay? It's, because it's sort of robust and it's not slow and it sort of, gives predictable results. And so I explain a little bit what it means. So first, this is this objective function, okay? This is what this objective function. Basically, at one point in time, I'll find the mean, the cluster center for those points, and the cluster center for those points. And that's a pretty good clustering, right? So basically, I really was able to identify the center. I found two clusters which are very separate, and they all group around their sort of centers. Okay, so basically, this essentially what it will do, it will take this cluster here and find the distance between the points to the center. And then it goes to this cluster here and finds the distance between the points to the center and adds all this up in this here. So this basically for each cluster I go compute the distance from the points to the center and do this for all the clusters. And then I come up with this J, this metric that defines how well I do. So obviously I did really well because these distances are very small, right? If this point here would be just by accident would be named to be part of this cluster, then this distance from here to here would be very large. Right? So basically, then that would not be such a good clustering because the objective function would be much higher. Okay. So, but how do you get to this point? Okay, seems to be so. So basically, this k-means clustering algorithm looks like this. You'll basically beforehand you decide, okay, how many clusters do I expect? Okay, and you name that, you call that k. And then you're gonna initialize k cluster centers, because each cluster has to have a cluster center. I'm gonna just randomly assign k cluster centers. And then we're gonna keep trying out, find out which points currently belong to each cluster center, which are basically have the smallest distance to that cluster center as opposed to all the other cluster centers. I'm gonna color them in the cluster center's color. And then I'm gonna re-estimate the cluster centers and then I'm gonna run that again over and over again until I find a minimum of the objective function. So here this is how it works. Okay, so basically here I have these points on the two-dimensional points, and I wanna figure out how they cluster. Can you see how many clusters would there be? Okay, well, actually not clear. How many clusters there might be. Are there going to be 3 or 2 or maybe 4? Let's try out. So let's say, okay, let's set k to 3 and just randomize them, put them somewhere. Okay, k1, k2, k3, and then do this thing that I told you about before. Let's figure out for each point which cluster center it's closest to, and color it in that color. Okay, so obviously this guy here and this guy here are closest to k3. This guy here are close to k2. This guy here is probably close to k1. This guy here, I'm not sure. Probably k1. This guy is all close to the k1. This one, maybe k1. Let's see. Okay, here we see that these green guys here belong to k1. These red guys here belong to k3, and these sort of maroon guys belong to k3, and these red guys belong to k2. Okay, we found the clustering, but now. Is this K really a cluster center of this cluster? Really not, right? Is K3 really a cluster center? Because we told you, right, this K must be in the center. Okay, but it's really not, right? So I gotta move it. Let's move it. Move it to the suffice just to find the average of all these points and move the point there. Okay, move the cluster center here. Okay, I've done it now. Now I have a new cluster center, and I'm going to look for the points again and see, well, is this point really close to K1 or is it close to K3? So basically computing the membership of each point to those new cluster centers. And I'm going to find out this one. And I kind of keep doing this until I don't improve my layout anymore. Okay, and I call that basically, the optimal cluster for this particular set of K. Okay, and basically this is it, right? So what's nice about this is, in 3 iterations, I discovered this clustering, and it was pretty relatively efficient. If there is K equals so many clusters and T number of iterations, then KT is much less than N. It's very simple to code. You can code this like in an afternoon. This is basically 3 loops. 3 loops, the number of points, the number of clusters, and then figure out when it converges. Okay, and that's it, right? And then have a loop, have a part that recomputes the K locations, and have a part that recomputes the coloring of the points. Very simple to code. You can do this in, if you applied for Google, you would have to do this in 2 minutes, to figure this out how this works. So, okay, so now the weaknesses for this is that, the problem is you have to figure out what K is in advance, but you don't know that. So you have to basically try the different K, by many different ways, and basically just try by trial and error, So and then also, you don't really know if your clustering given a K is really the best. You'll have to also try a few clusterings with a given K to make sure it has converged the best way to avoid the local minima and optimize for the global minima. Okay, so basically this. So how can you find the best K? So this is actually a very simple method. You can basically go like this. Okay, so you have this one here, or this one here. So K equals 1. Well, this is a terrible MSE because this is really not a center. Right? K equals 2. Yeah, this is MSE 173. Test much better than for K equals 1. It is a much better cluster. So this seems to be a pretty good representation of this. And here, if you use 3, then you basically subdivided this cluster here into 2 more clusters. And it has improved a little bit. The MSE has improved a little bit. Of course, how can you get the best MSE? If you choose K equals N. Because then every point is its own K, and the distance of each point to its own K is 0, then the MSE will be 0. Of course, that's not going to be clustering, right? Because now you just, kept the same points again, so you haven't reduced any data, right? And have not really done anything, right? So this is really, there's like a sort of a trade-off between the number of K you choose and the error you're going to maintain, okay? So how do you find out, right? We have a winner, but is it really that a convincing winner? This one is really a very good winner, right? I mean, this has like almost 7-fold, right? And here, just a little bit more. This is a clear winner, but just by a hair. Okay, so when do you stop looking, right? Then you try to find the right K. Okay, so what you do is like this. You'll try out, basically find out. Usually, what happens is there's always going to be like this kind of function. There's always this called an elbow function. It's always like this in many other optimization tasks too. You always sort of get this sort of, when you have a parameter, the hyperparameter, you change it, and things get really get much better very fast. And then you get a little bit of an improvement as you choose the hyperparameter higher, right? But not that much, right? So it's basically typical elbow curve, happens everywhere, right? So you make initial improvements are very drastic, and then overall, as you make more improvements, it doesn't really matter that much, right? So you're gonna find the elbow. That's the key. You gotta find where is it without having to try all the Ks. So what you're gonna do is you're gonna basically try a few Ks and estimate that, right? So basically try this one here, find the tangent, find this curve here, then move it here, and this is the elbow, right? Basically, plot this curve, and then this is basically your elbow that you find. Okay, it's not here, it's here. Oftentimes, it's not that clear what the elbow is. Sometimes it's really sort of gradually changing, so they can use this method to figure out where's the optimal K. Maybe you can go one up, one more higher, but usually this is a nice way to find K. Try all those out, or try a few of them, and then find out where it's nicely bent like this. Okay, and this is really the K. It's called knee finding. Okay, so this is basically what you would use in K-means clustering. You would try to find the K using this elbow method, and then you know for sure this is a good K. Before you never quite knew, right? But now you know it, and you can sort of assume that it always gets better like this. Then we talked about this last time, how to use the data. Basically, instead of random sampling, where you just pick random points, you'll do first a K-means clustering, which is basically these points. These clusters are called strata. That's why it's going to be called stratified sampling, what I'm using. And then I'm gonna basically pick a percentage of each cluster, to subsample by this percentage. Okay, so if I wanna keep 80% of my samples only, then I'm gonna reduce cluster number 1 by 80%, or 2 by 20%, cluster number 2 by 20%, cluster 3 by 20%, and then I basically have not removed any of them. I have not caused any bias, right? I just subsampled each of them, sort of similar ways, right? So I haven't really introduced any bias. I don't want to introduce any. I do not want to, remove any outliers. So I'm gonna only use clusters with membership greater than 7 or something like this, or 4, whatever you like, whatever you call an outlier. So you don't lose the outliers. Okay. So this is basically what you wanna do. Okay. So now let's talk about attribute reduction. Okay. So I was actually not thinking that I would get that fast, but far. But let's talk a little bit about attribute reduction. Okay, we have some more slides next time around, but this may work. So basically, attribute reduction is one way. You want to basically figure out where is my variance the biggest, along which dimension is my variance the biggest. Okay, so I can use what's called, and probably many of you know this. I just present it to make sure that everyone knows it. Those who haven't taken the data science course, for everyone else, probably very boring to talk about principal component analysis. Okay, so basically, you want to figure out where is my largest variance. And we're going to basically figure out and find the new coordinate system that represents this variance the best. Okay. So eventually you want to find out the covariance. Okay, you're going to find out that this is the negative covariance, low covariance, positive covariance, or correlation, same thing, right? Just right. Okay, so basically you want to find out for n variables, you have n square variable pairs. Okay, and you're going to make this covariance matrix that measures basically for each variable pair measures how big the covariance is and puts it here, right? So this is the covariance of attribute 1 with attribute 2, and this is really the same as the covariance of attribute 2 with 1, right? Because it's the same two pair of attributes. It's just flipped. And then here along the diagonal. That is the variance of the attribute that's itself. Okay, it is the variance itself, just one-dimensional variance. How much do the values fluctuate within a certain, within one direction? Okay, then you make this covariance matrix, and then so basically that's how you compute it. You find the mean, and then one attribute, find the mean of the other attributes. And then take the attribute 1's value and attribute 2's value, subtract it, do this for all the attributes or for all the data points of that x, y pair, and divide it by the number of points, and then you're going to get this covariance. okay, between X and Y. Do this for all the pairs, okay, and then you can build this matrix. Or you can do the correlation, which is really the same thing, just normalized by the individual variances for X and Y. So basically it looks like the same thing than before, just subdivided by the individual variances here. This is like individual variance of attribute X, variance of attribute Y, and standard deviation, basically take the square root of it, and then, that's basically correlation power. So essentially, it just removes it makes it more homogenized, right? It like removes the spread of the individual attributes, makes them standard. That has some advantages, right? So, then you have this, right? So the ultimate goal is basically to find a coordinate system that sort of can capture this variance where it is in the high dimensional space with as few axes as possible. Okay, so basically this is like one picture that you may get in 2D. You get like this along here. There's a lot of variance. There's a lot of stuff happening here. Along here, not so much. Okay, so basically, if you want to compress it to only one dimension, maybe you don't need the red dimension. Maybe you can just use the blue dimension only. Then you have like 50% of the question. Because you got rid of one dimension completely. Now, one problem with that is, of course, this blue dimension isn't really any more meaningful, right? If these two dimensions of this coordinate system were like income and tax return or something like this, this here is just a mix of those two attributes, right? So they really don't have a lot of semantic value to like someone who would just look at the data itself, but it's but if you want to look at clusters in a low dimensional space, then that's not a bad thing. Remember k-means, right? For example, k-means you have to compute distances, right, between two data points. You've got the Euclidean distance uses all the different attributes, right? Attribute between attribute 1, 2, 3, 4, 5. So the higher the higher dimensional spaces, the more complex this distance calculation becomes, right? So if you want to do clustering, you want to do that in a space that has lower dimensionality than before, right? So if you want to just find clusters, then doing first a principal component analysis to reduce some of the dimensions and then do the clustering can bring some advantages in terms of computational complexity, right? Because for clustering you don't really care what the clusters really are, right? You just want to figure out where the groups of items, so you can look at them. You can always go back to the original space later on, but basically that's where principal component analysis is really helpful to identify clusters at a small amount of cost, and actually you can, if you reduce the dimensions to 2, then you can actually easily visualize those clusters too. Okay, so basically this is basically why principal component analysis is a good thing. So let's look at it a little bit more, how it actually works. Okay, so this is the first principal component. It's the one along the largest variation. The second one, and then basically how it works is basically you take this covariance matrix or correlation matrix, whatever it is, call it C, and you'll do a QR factorization. Like, you basically SPD of some sort, LU decomposition, to figure out this kind of three matrices. This is the matrix with the eigenvectors, and this is the matrix with the eigenvalues. And what the eigenvalues really are, I think I have a slide here what it shows you. So the eigenvectors tell you in an ordered way, like it tell you like what are these x's in high dimensional space that go along these large variances. Okay? Basically, it's just a bunch of vectors that describe this new space that is variance oriented. Okay, and this matrix in the middle, this eigenvalue matrix, is a diagonal matrix only where these eigenvalues just tell you how long these x's are. Let's see an example. Okay, so here when you look at this. This is the eigenvector here, which is a combination of these original vectors, basically 0.5 this, 0.5 this in this case, and the length of this, the spread of this distribution is the lambda 1. This basically tells you how wide this distribution is. Is this the length of the vector? Okay. And then you have another one here, lambda 2. Of course, this lambda 2 is much smaller because here there's not a lot of length, right? The lambda 1 is really big. Lambda 2 is small, and these two vectors are orthogonal, right, by definition, because SVD will give you an orthogonal matrix, and then these vectors are always orthogonal. So in 2D you're going to only get 2. If you have 3D, you're going to get 3 vectors. If you have 4D, you're going to get 4 vectors. 5, you're going to get 5 vectors. And then depending on the lambdas, you can get rid of some of these vectors. Okay, so basically that's how you would do it. Okay, then to show you how this, like a little bit more an example for PCA, is basically this one. So let's say you have this distribution here, variable 1, variable 2, and you find these principal components with this covariance matrix orthogonalization. 1, this PC2. Then you take this space here and basically convert it into this principal component space. All you really do is just take this and just align that with the x-axis, align that with the y-axis, and plot the points like this. So now you can see a clear orthogonality, right? You can see like there's a lot of variations here, a lot of variations here. Looks like an ellipse that is aligned with the axes. Okay, no longer like an ellipse that sort of hangs out in the space. Now it's an axis-aligned ellipse. So this is basically, if you look at the ellipse representation as a quadric, there's going to be only the diagonals are occupied and the non-diagonals are empty. Right? And basically, when you look at this now, you can say, okay, you can take the lambda 1 plus the lambda 2. You can take these two values, which are along the diagonal of the eigenvalue matrix. You add them up, and this becomes the trace of this matrix. And then you can compute the percentage of this value with respect to the overall trace, right? So now you take 9.87 over 12.9. That's basically 76.5% of the trace is captured in lambda 1 in the first eigenvector. And you basically say 76.5% of the total variance is explained by this particular eigenvector. And then the remaining 23.5 are essentially explained by the second lambda 1. And you can see it's actually relatively small compared to this one. It's basically a third, basically, which makes, which essentially here, basically 2/3 are explained by the first one and second, So basically this gives you a way to do it, right? Now you can say, well, I'm okay with just explaining 76.5% of my variance. I don't really care about the other stuff, right? This is just noise, right? So I don't care. So I'm going to get rid of this, and now basically compressed it nicely, right? You can basically now create these sort of plots, which is called a scree plot. And the scree plot plots a histogram of these principal components. So basically just order them by the lambdas. Okay, so let's say in this case you have a 7-dimensional space. We built the covariance matrix or correlation matrix out of it. We did the principal component analysis, we did the LU analysis, the SVD, the orthogonalization. I found the principal components in the one matrix and the eigenvalues in the other matrix. Then I reordered the principal components by the lambdas, right? And then here are the lambdas, right? So this basically shows this lambda, the first lambda of the lambda of the first principal component is pretty high, basically 40%. Second one is 15%. Third one 15%. Fourth one 12%. 10, 8, 7. So basically what I find out here essentially is, this one is dominating all the others, right? This is almost 40%. This one is 15%. So basically my main variation is really in the first principal component, and then the other ones have also some variance, but not. This is really dominating my spread, okay, of the data. So I can take any threshold here, right? So this is basically cumulative variance, right? So basically every vector, here's the Strauss's growth, and the growth gets smaller and smaller as I move over. So I can say like, okay, I want to explain 75% of my variance. If I want to explain 75% of my variance, I need to maintain 4 of my eigenvectors, like 1, 2, 3, 4. Okay, and if I want to explain more variance, then I have to keep more eigenvectors. If I want to keep 100%, I have to keep all of them. So basically, that's basically sort of a nice visualization of the variance that you can keep, the trade-offs you can make by keeping more or less of my principal components. Okay, so the scree plot is a very important visualization when you deal with principal components. So And so I want to basically give you a little bit of a teaser for next times. So basically the eigenvectors, they're combinations of the true data vectors, right? So, but they're not really meaningful to explain the data to like in terms of the vectors themselves, in terms of the attributes themselves. All they really do is they give you these alignment vectors, but they're always sort of combinations of the original attributes, right? And they're like not that meaningful if you're going to really create like a business strategy or something like that, or explain it to someone, like what is actually going on in terms they understand it, like in terms of attributes. Then a principal component analysis is a little bit of an awkward thing to have, okay? Because all you have is like these arbitrary vectors in space, that don't really mean anything. So what you want to do is basically you want to find the loadings, okay? The loadings of the space. That the loadings are those vectors that are most dominant. These are these attribute vectors that are most dominant in your principal component space. Okay, so this is a little bit too long now to talk about in the remaining 5 minutes. So I'm gonna not talk about it. I'm gonna stop here, okay, and then defer this to next time.